If Gemini or your favorite GPT is the brain to your app, then Firestore is the backbone and its long-term memory. Without it, your app is basically a goldfish. Today, we are giving your app the power to remember everything, synchronize in real time, and work even when you are offline. Amazing, right? Stop building temporal vibes and start building software that lasts. Let's get to it. Module 3. Data Management with Cloud Firestore and Real-Time Database. Understanding NoSQL, collections, documents, and fields. Core differences. Firebase offers two distinct NoSQL databases, Cloud Firestore and the Real-Time Database. Real-Time Database. Firebase is original, stores data as a single JSON tree. It's great for simple data and applications that require low latency, real-time synchronizing of state across many clients. In contrast, Cloud Firestore is Firebase's modern database, storing data in a more structured and hierarchical format of collections and documents. Firestore is built for more complex data models, richer queries, and better scaling. Its billing is based on operations, that is, reads, writes, and deletes, while real-time database charges for bandwidth and storage. Firestore also offers better offline support for web clients. A collection is a container for documents. It's the highest level of organization in a Firestore database. You can think of a collection as a folder or a table in a traditional database. A collection contains only documents and no other field or data directly. For example, you might have a top-level collection named users to store all documents. A document is a fundamental unit of storage in Firestore. A document is a lightweight record that contains a set of key value pairs, which are called fields. A document can also contain sub-collections. Documents in a single collection don't have to have the same fields, which make Firestore a schemaless database. Think of a document as a row in a table or a JSON object. Fields and data types. A field is a key value pair within a document. Firestore supports a variety of data types, including basic types like string, number, boolean, and array, as well as more complex types like map, a nested object, timestamps, and geopoints. Using correct data types is essential for proper querying and data integrity. For better understanding, I'll provide some insights about the various data types mentioned. String, a sequence of characters such as letters, numbers, or symbols used for storing text. Number, a numerical value. This can be an integer, for example 100, or a floating point number, for example 3.14. Boolean, a data type with only two possible values, that is true or false, used for conditional logic. Array, an ordered list of values. The values within an array can be of any data type. Map, a collection of key value pairs, similar to a nested object or dictionary. It allows for structuring complex data within a field. Timestamp represents a specific point in time, including the date and time. It is typically used for tracking when data was created or lastly updated. Geopoints, a specific geographical location presented by latitude and longitude coordinates. So each data type here can be used depending on the scenario or what is intended to be achieved. Data modeling best practices. Flattening versus nesting. A crucial concept in NoSQL data modeling is deciding between flattening and nesting data. Nesting involves storing related data within a single document, often using a map or array. This is efficient for small, tightly related data that is always accessed together. However, nesting too deeply can make queries complex and inefficient. Flattening, on the other hand, involves creating separate top-level collections for related data. You would then use the document's ID to link them together. This approach is highly recommended for Firestore, as it allows for much more powerful and flexible querying, avoiding document size limits and improves performance. Handling relationships. Because Firestore doesn't support traditional joins like SQL databases, relationships between documents are handled by sorting the ID of the related document as a field. For a one-to-one relationship, for example, a user and their profile, You would store the user's ID in the profile document for a one-to-many relationship. For example, a user and their blog post. You would store the user ID on each blog post document. For many-to-many relationships, you would create a third collection that acts as a join table, storing the IDs of the two related documents. Denormalization and redundant data. In a relational database, you avoid duplicating data to maintain consistency. In Firestore, it's often a best practice to denormalize by duplicating data. For example, when a user posts a comment, you might store their name on the comment document itself, in addition to it being their user document. This allows you to display the comment with the user's name in a single read, avoiding a second query to the user's collection. While this creates data redundancy, it significantly reduces the number of reads, which makes a key factor in Firestore's pricing model and performance. Aggregating data. When dealing with a collection of items, for example, like on a post or comment count, querying all the related documents and counting them is inefficient. Instead, a document pattern is to aggregate the data by maintaining a counter field on the parent document. For instance, a post document could have a like count field. When a user likes the post, you increment this field. This allows you to get the like count in a single fast read operation. Real-time data synchronization and offline capabilities. Real-time listeners. One of Firestore's most powerful features is its real-time data synchronization. By attaching a real-time listener to a document or collection, your application will receive live updates whenever the data changes in the cloud. You don't need to manually check for updates. The database automatically pushes the new data to your application. This is ideal for building collaborative apps or live dashboards. Handling snapshots. When a listener receives a new update, it delivers a snapshot of the data. A snapshot is a read-only presentation of the data at the specific moment. When listening to a collection, the snapshot also includes metadata about the changes that occurred. For example, which documents were added, modified, or removed. Your application can then use this information to update the user interface efficiently. Client-side caching. The Firestore SDK maintains a local persistent cache of the data that your application has recently accessed. This is a powerful feature that enables two things: offline functionality and latency compensation. For offline access, the app can read from the cache even without a network connection. For latency compensation, any write you perform is applied to the local cache immediately, making it feel instant to the user even before the data is synchronized with the cloud. Offline to online transitions. When a device is offline, any write you perform are stored locally in a queue. When the network connection is restored, the SDK automatically sends all the queued writes to the database in the correct order, that is chronologically. The app's real-time listener will then update with the final state of the database, ensuring that the data is consistent across all clients. Querying, filtering, and ordering data. Basic queries. The most common way to query data is to filter it using a query function clause. This acts as a filter, allowing you to retrieve only the document that meet a specific condition, whereas documents where a field is equal to or is greater than a certain value. Chain queries. You can chain multiple query clauses to perform more specific queries. For example, you could query for all posts with a specific tag and an active status. However, a key limitation is that you can only use one inequality operator, for example, greater than or less than per query. If you need to filter a range for multiple fields, you need a different approach. Ordering and pagination. To control the order of the results, you use OrderBy function. For large data sets, it's not efficient to retrieve all documents at once. Pagination is a solution where you fetch data in manageable chunks. You use limit to specify the number of documents to retrieve per page and a cursor, often the last document from the previous page, to mark the starting point for the next page. This ensures your app is fast and responsive without being overloaded. Understanding indexes. Firestore requires an index for every query. An index is a special data structure that allows the database to find the documents that match a query without scanning the entire collection. Single queries, like a single where clause, are automatically indexed. However, for a more complex query, for example, combining multiple where clauses and OrderBy clause, you will need a composite index. A composite index is a database index created on two or more columns of a table. It's also known as a multi-column index. Instead of speeding up searches on a single column, it optimizes queries that filter or sort data based on a combination of those specific columns. Creating indexes. If you attempt a complex query that doesn't have a corresponding index, Firestore will return an error message that includes a link to automatically create the required index in the Firebase console. Alternatively, you can create them manually. This process is crucial for enabling and optimizing complex queries and ensuring your application's performance as it scales. The engine is set, your app finally has a memory that doesn't quit. You've moved from a chatbot to real-life software. But theory is nothing without action. In the next video, we are building a real-time to-do list using everything we just learned. So get ready to ship your first agentic app. Do well to leave your thoughts or contribution in the comment section. Like, subscribe, and I'll see you in the next video. Cheers!